We can wait for few minutes, then you can
Yeah,
start.
sure. Rohit,
Yes, sir.
I have requested Rajni Pandey also to be presented today.
Yes, sir. Uh, I think she joined, but she left. Maybe.
Maybe so.
Yeah.
She said that she will be there.
Oh, yeah.
So
No. She's
any
there.
question now today people can ask about any questions on any portion of the course.
Okay. So, yeah, we have some students. So, hello guys. So today all the three instructors are here present. So you can ask from any lectures, any doubt that you have, and because this is the last live session of for this semester, so it's better to get everything clear. So, sir, if you want, you can maybe start because it's already 5 minutes past to 4 p.m.
Okay, so I uh, I just wanted to point out the mistake we had in one or two lectures, and that was connected to these DC accelerators, and that is shown here. That you in one of the lectures you must have seen that where I have discussed voltage measurements, and one of the ways the voltage is measured on the high voltage terminal. This is the high voltage terminal, and the voltage was measured by this formula, which is V into IR. R is the total resistance across the column section, which is shown here, and I is the current passing through this. So V, the voltage will be I current passing through this, and the R is the total resistance. So this was, now in this win, we have shown the picture I have shown is here, which is seen here on the right hand side, and there is a small error in this one, that if you have this plate like this, which is continuous from this end to this end, and I've shown that this is pressure vessel which is grounded, and if the high voltage plate is touching this, then this terminal will not get the voltage, and therefore it should not touch. So this correction has to be done. This was done here in this figure, That means in this section, this plate is only from this portion to this portion, covering only the high voltage part of it. This is the high voltage, and the plate is only this portion, and here there is nothing. So this, if you call this is called column section, high voltage column section. This is standing alone. This is not supported anywhere. Is supported only at the bottom. So if the resistance uh, uh, across the whole thing is R, which is n is the number of gaps times R dash. R dash is the resistance between the two plates. Then it will be given by V is equal to IR, which is same. Rest remains same. And then what we do is, how will you measure this current? This was not showing in the earlier one. See, here it was looking like as if it is not, it is hanging. So this last plate has to be grounded through a meter, where that meter is emitter here. You can see on the left hand side. So there is a emitter here which measures the current, and it is put in the series of the resistance. Now you might wonder that if uh, meter is also having a resistance, then the total resistance will not be N into R dash here, but that also will get added. But what happens that emitter has a very low resistance, and one shunt resistance is put in parallel. So the main current passes through that. So actually emitter is nothing but a galvanometer where in plus a shunt resistance. So the most of the current passes through the shunt resistance, and a very small current passes through the galvanometer, which is measuring the current by deflection method. So you can say that you can put this in the series of this resistance, and since the shunt resistance of this, or you can say internal resistance of this meter, which is ammeter, is very small as compared to this total resistance. So no change in I is observed. It will be there because of this additional meter put in series, but it will measure the current. So this is the actual figure instead of this which we have shown here. And rest remains same. So there were two changes which I thought I should mention. They are practical changes. One is that there is no connection here on either side. So this was called base plate, on which this high voltage terminal is kept, and this is not touching the pressure vessel. Otherwise, because the pressure vessel is grounded, no voltage will be generated, and therefore you cannot measure it. And you can't even measure and you can't generate any voltage on this. So the base plate is only up to this point to this point, and not up to this point. So this portion is not there. From here to here, here to here. I have told this earlier also, but I thought I should repeat it, and the rest remains same. So this was one. And there was one question which many people get confused. So I thought I should clarify this. See, there are three kinds of accelerators. One is a DC accelerator, other one CW accelerator, and third one is a pulsed accelerator. most of the people, 95% of the people get confused between this CW and the pulse accelerators. So difference is here that if you see the voltage in this is DC accelerator. So if you plot I, which you get at the output as a function of time, then this current is there all the time. And that is because this VT voltage is also there all the time. So current ions are extracted all the time. So if you take the average current of that, average current, average current is nothing but I max, which is this, into the duty factor. Duty factor is a ratio of the time for which the current is there divided by 1 second. That means in 1 second, how much time current is there. So duty factor is time for which current is there out of say 1 second. So in DC accelerator, because it is there all the time, suppose you take 1 second here, then it is there all the time. So that means duty factor is 1. So that means duty factor is 1 means I average is same as the I max. Suppose this is I max, so it is I max is same as that. But that is not the case. So for example, if you take uh, RF accelerators, either linear accelerators or cyclic accelerators, where the voltage is applied as a cyclic one, sinusoidal wave or any form of wave. So, as has been explained in various lectures, that there is a synchronous phase, and let's say this is the synchronous phase where the beam, when injected, will see only that it will be accelerated only at that these points. On other point, there will be of course delta V, delta phi. So if you take this x-axis, either it is t or it is delta or it is phi. So the delta phi will be, this will be a synchronous phase. So beam will be accelerated only at that point. See, if the beam is accelerated on this portion, it will be accelerated only in cyclic accelerators. So that means synchronous phase is on the rising portion of the pulse in the case of Linear, and falling case, and that I have explained in that. In this case, because beam is suppose, let's say the accelerator is having 1 gigahertz, or let's say 252 gigahertz uh, is the frequency of that. That means there will be so many pulses. So I just for the sake of comparison, I have calculated here. Let's say RF, you have a RF accelerator, either cyclic accelerator or linear accelerator, and it's working, let's say, at 100 hertz. That means there are 100 times the beam is seeing the synchronous phase. And each pulse, let's say, you can see that it will be accelerated here. So at the output, you will see the pulses here, which are shown here. Let's say this is 1 second here. That means 1 second, there will be 4 pulses only. And now if it has 100 hertz, that means in 1 second, 100 pulses will be there. Let's say the pulse width here, pulse width is about 400 microsecond. Then the total time beam is there at the output out of 1 second will be 100 into 400 microsecond. So duty factor will be 100 into 400 into 10 power minus 4. out of one side. So duty factor is always in percentage. So it will be like 4 into 10 power minus 2. So it's roughly like is called 4%. 4%. So average current will be if the maximum peak current was 10 milliampere, then it will 10 into 10 power 4 into 10 power minus 2. So it will be only zero point 0.4 milliampere. So you can see that although the peak current which you have injected into the accelerator is 10 milliampere, the average current at the output, which Faraday cup or any device will measure, which measures the average current, will be only 4 point milliampere. So it is very small. So that is why these cyclic and linear accelerators have to work at high frequency, and so that the average current also becomes high. But that is not possible. For example, if you take very high energy accelerators, there the average current is not very important. There the energy is important. So therefore, even you get only one pulse in 5 minutes or something, but the energy will be so high that there will be a lot of reaction taking place, and that will be good enough to them. So in some cases, the average current, high average current is required. Energy is not very important, but in some cases, you need very high energy, but average current will be big. So only one or two pulses once in a while, and that itself gives so much of data that a lot of reactions takes place. Even secondary reactions take place. Now, if you take the third case, which is a pulse accelerator, it is not necessary that injection is done at each cycle once. It is not a. So what you can do is you can inject once in a while. So that means in this case here, it was injected here. So one pulse here, and the other pulse is not in each cycle, but it is after 1 second. One pulse is injected from the ion source. So you see at the output, you will see a pulse here, accelerated beam pulse here, and after 1 second, again one pulse will. It need not be every second. It can be each hour also. So in the beginning, one pulse is injected, and after 1 hour, another pulse is injected. Here, for example, in this figure, we have injected one pulse every second. So the current here, if you see the average current here, will be duty factor will be 1 into 400 microsecond, because so I'm assuming that 400 microsecond is the width of the pulse. So 410 power minus 6 is same as here. Instead of now 100 hertz, it is now 1 hertz. Only one pulse in a per second. So it will be 1 into 10 power 1. This is wrong actually. This is 10 milliampere current. So if you take 10 milliampere current, which I have taken in this case also, so it will be 10 milliampere into 4 into 10 power 6. So it will be 0.004 milliampere. So the average current has come down by a factor of 100 here, because the frequency of the accelerator has come down by a factor of 100. So the average current here is, so these kind of accelerators, pulse accelerators, are very useful where current is not very important. But it is important to have the high energy. For example, CERN, if you take, there it is not important that how much current you have, average current you have. peak current may be very large. In that pulse, the current may be very large. Because suppose if you have very small pulse, nanosecond pulse, peak current may be very large, but the average current will be very small. So, and that is the requirement there. While in the case of some uh, uh, accelerators where irradiation work is done, or for example, if you take ADS, accelerator driven system, where the output depends upon the how much is the average current, and there you would like to have this frequency of the accelerator should be large so that the average current is large. There is a CW. Each wave wave will have at least one. Will have this is one cycle of the wave, and the frequency, let's say, normally is, for example, proton accelerator is about 250 megahertz. So that means each second there will be 250 mega times, million times pulses will be there, and therefore average current also will be large. And it will of course depend upon what is the uh, so if suppose somebody says that he has accelerated 10 milliampere current on that, that means he is saying that it is 10 milliampere peak current. It's not the average. Average current may be low. So that we have to keep. So this is the difference between these three kind of accelerator. For example, normally this people get confused between this CW and pulse kind of accelerator. So this is the difference between pulsed and the CW accelerators. And this is a DC accelerator. DC accelerator duty cycle is one. Here duty cycle may be very small. For example, here this duty cycle is really very small. So this was the difference. I thought I should clarify. So thank you very much for this. Now, Doorbell thing can start.
Thank you, sir, for clarifying this. If anyone has any question, they can ask. He said you can click on stop present. Yeah.
I hope I am able to clarify these things because most of the people have confusion between CW and pulse accelerators.
Hi, sir.
Yeah.
I'm having doubt in SRS actually. Can I ask it now?
Which one?
SRS, cyclotron radiation source.
And this Amlesu will be there. Amlesu taught that the module 3, no? Amlesu?
Yes, sir, I am there.
Yeah, so now you can ask, he will be able to take care.
Okay, sir. Sir, so basically, what is the difference between SRS and normal electromagnetic source? Because both are going to give a same electromagnetic source, right? But I don't think this SRS is going to give a monochromatic light. So why? What is the use of using this synchrotron source?
Actually, in normal laboratory source, you can get X-rays very well. Just impinge the electrons on some target and you will get bremsstrahlung radiation out of that. This is basically a very small tabletop X-ray sources. Okay. But if you will compare these sources with the SRS tremendous intensity. I can give you some example. Suppose you expose some sample using your laboratory X-ray source, and you are getting some data in, say, 3 or 4 hours. The same exposure using SRS can be made in just few microseconds. So you can estimate the intensity differences between these two sources. So intensity of X-rays emitting from the SRS is very, very, very high. You can say 10 raised to 5 to 6 order more. I am saying order. No? So that is the SRS, but definitely SRS are not monochromatic. They emit right from infrared to X-rays. So whole spectrum is also available. So if user wants different wavelength, they can just put their filter in the beam lines and then can tap the particular frequency of the radiation. So wide spectrum is another beauty of the SRS. In laboratory X-ray source, whatever you put the target as a target, the characteristic X-rays of those atoms or molecules will have high intensity, means you have discrete peaks, not a continuous spectrum. In SRS, you have continuous spectrum. So every frequency is available from the SRS. Just put the filter of your desired wavelength and get the radiation of that wavelength. Definitely in SRS, one more advantage is that the emitted radiation is polarized, plane polarized basically, in the plane of bending. Means the plane of motion, you can say, the electric field lies in that plane. So emitted electromagnetic waves are basically plane polarized. So if a user wants some polarization in their experiments, these are actually required if you will consider some study of magnetic materials or like that, then it is also useful. So from SRS, you have high intensity, you have polarized light, and you have very wide spectrum. So these three advantages make it distinct and unique too. And definitely there is one more class which is known as FEL, free electron laser, in which a electron linac beam is accelerated through electron linac, and that beam is passed through some special purpose magnets known as undulators. And in that case, you get even more intensity than the SRS based on the synchrotrons. Definitely, but you will get here monochromatic lights. That's why this is the laser. This is the free electron laser. The beauty is that here, by tuning the energy of the beam through linac or gap in the undulator magnets, means changing the field of the undulator magnets, you can tune the frequency. So you get a tunable laser here. So these two kind of sources are there. Definitely FEL was not covered in the lectures. Only synchrotron based sources were covered in the lecture. Okay, so I think now it is clear.
Yes, sir.
There is a question in the chat.
Sir, how RF wave focuses and defocuses? Please explain for higher momentum and lower momentum vertical with RF wave, as well as a schematic diagram of RF cavity. Actually, in lecture 31, there is even animation of these RF focusing. So I am just share the lecture 31 slides here. Just I am opening that.
Are you sharing, sir?
Yes, I am just sharing.
Okay.
Is it visible?
Yes, I can see it.
Yes, sir.
Okay. So now you can see that this is the RF wave. I can show something here. Suppose this is the complete periphery or path of the beam taken in the synchrotron, and at certain location there is the RF cavity. This is the RF cavity. And when electron or a proton or any ion which we want to accelerate, when it passes through this cavity, it gets accelerated. And this is the place where phase focusing takes place. Means focusing in the longitudinal direction. Definitely you can consider that RF cavity works as the quadrupole in the longitudinal plane. So how this takes place, we can see here. You can see that revolution time, basically, that is the length by speed. Now this length itself depends on the momentum. Means what momentum of your particle is, that the L depends on that, because we have dipole magnets and each momentum follows different path in the dipole magnet. Means path length changes due to presence of the dipole magnet. So this L is a function of momentum, and definitely velocity in the denominator is also a function of momentum. Higher momentum particle may have higher velocities, and lower momentum particle may have lower speed, and like that. Means if you have higher momentum, the bending magnet bends less or dipole magnet bends less. Means L will be higher because it will go on the larger radius of curvature path, higher momentum particle. So L increases in general with the delta P by P higher. Means if momentum is higher, L will be higher. And at the same time, denominator will be higher also, because higher momentum particle have higher speed. So this revolution time actually basically decided by competence between these two variables, how these are changes with the momentum. L also increases and beta C also increases. So definitely this we can say delta T by T means how it is changing. It will be delta L by L minus delta B by B. So these are two competing factors. One factor is increasing, delta L by L is increasing the revolution time, while delta B by B, if it increases, it decreases the revolution time. So when this dominates, we have delta T by T positive. And when it dominates, we have delta T by T negative. So we say when this quantity is positive, the machine is above transition. And if this quantity is dominates, then delta T by T will be negative, and we say that machine is operating below transition. And when these two quantities become equal, means revolution time becomes independent to momentum, we say that this is the isochronous mode of the machine. And we are saying that synchrotron is operating on the transition. Definitely delta L by L, it is present only in the synchrotron, not in the Linux, because Linux do not have bending magnets in between. So all the momentum follow the same path length. So this delta L by L is not there in the case of linear accelerators. There is only delta beta by beta. So this delta T in that case, instead of revolution, I will say delta T of the travel will depend on this factor only, and this will be negative. In case of synchrotron, it may be positive, it may be zero, it may be negative. In case of cyclotron, it is certainly zero because we are in the non-relativistic regime, and we have seen all these in our first lecture. So if we divide this by delta P by P, we will get how the revolution time changes with the fractional momentum offset. Now we see how RF phase actually focuses it. Now suppose we have three particles distributed in the RF wave, means the arrival time of these three particles are different. One particle is leading, red particle may lead the black particle, and this purple particle may be lagging behind it. So these are reaching a different time in the RF waves. So you can say that black particle, you can consider it is a synchronous particle. Means after one turn, it will again come on the same phase. Synchronous phase is defined in this way. Actually, the phase which does not change after revolution, that phase is itself synchronous phase. So means energy and revolution time is perfectly matching. Means how much energy is changed, that is exactly matching the revolution time with the RF time period. This is known as synchronism. So this phase is that phase where this synchronism occurs. So this is the synchronous phase. So this particle after one turn again comes here. Now what will be about this red particle? Because it is at higher potential in the RF voltage than this synchronous particle, it means it will gain more energy than the synchronous one. Now if it has more energy, means delta P by P is higher or plus or positive. Now consider what will be the revolution time. If it is above transition, the revolution time will be more because delta T by T is positive in this case. And if it machine is below transition, then this red particle will reach earlier. Means it will have faster speed and it will reach closer to the synchronous phase. And same will happen to this particle because now this has gain lesser than the synchronous one, means its revolution time will increase and will, instead of coming here, it will come here. So it will reach closer to the synchronous particle. And in this fashion, on next turn, it will come more closer and closer in successive turns, and we get the focusing. Now suppose we have these three particles on the falling edge of this RF wave. What will happen? Again, here we will follow the same analogy. This is the synchronous phase. Black particle is on the synchronous phase. Now, because this red particle is getting more energy, it will reach early. So the gap between the synchronous one and the red particle will increase in the next turn. And similarly, the purple particle has gain in energy lower than the synchronous one. So its revolution time will be decreased than the synchronous one and it will reach here somewhere. So gap between these three particles increased in the next turn. And in successive turn, this gap will also again increase and increase. So we have a defocusing in this case. So in this fashion, depending on the transition energy, means whether the synchrotron is above transition or below transition, we can get focusing in the rising edge or falling edge. In case of LINAC, because delta L by L term is 0, we get focusing in the rising edge only. So I think now you can see that focusing takes place on one edge or rising edge, then defocusing will be on the falling edge. In case of above transition machine, this whole scenario will be reversed. Means on the falling edge, phase focusing will occur, and on the rising edge, there will be defocusing or debunching. So I think now it is clear to you.
Thank you, sir. So, Dhanush, do you have more questions?
No, sir.
So I want to know if Pratham, if this clarifies your doubt or not. Okay. Rohitji, now we can share the solution of detailed explanation
Okay,
of
sir.
the solution of last assignment.
Okay, sure.
Okay. So in the last assignment, we will take one by one, and all the problems will be discussed here. So is it visible?
Yes, sir.
Okay. So this week, mainly different types of synchrotron and storage rings were discussed. As an example of electron machine, we discussed the synchrotron radiation sources. As an example of proton machine, we discussed the spallation neutron source. So the problem, we will come one by one on the all problems. The problem one was an alpha particle at 500 MeV is passing through a quadrupole magnet at a distance of 10 mm from the design path. Means particle is deviated 10 mm from the design path in the horizontal direction. So you can say this is x. X is equal to 10 mm. What will be the change in angle of the trajectory by this quadrupole? If effective length of the quadrupole is 100 mm and the field gradient is 10 Tesla per meter. Assume quadrupole magnet as a thin lens and consider the rest energy of the alpha particle as 4 GeV. So definitely the given data are x is 10 mm is given, effective length of the quadrupole 100 mm is given, and gradient 10 Tesla per meter is also given. The rest energy of the alpha particle is 4 GeV, and kinetic energy which is given of the alpha particle is 500 MeV. So we have converted all the energy into the EV. Now in thin lens approximation, the change in angle is just KLX. K is the normalized strength of the quadrupole, means gradient of the quadrupole divided by beam rigidity. Beam rigidity is just P by Q. P is the momentum of the particle and Q is the charge on that particle. L is the effective length of the particle. X is the deviation from the design path. So deviation of the design path is given as 10 mm. L is given 100 mm. G is 10 Tesla per meter. And Q and P, P by Q, we will calculate this thing. So for calculating the P, we will calculate using 500 MeV kinetic energy. So first we will calculate the gamma, that is total energy by rest mass energy of the particle. So total energy will be 4.5 GeV. 4 GeV is the rest mass energy, and 0.5 GeV is given the kinetic energy. So total energy is 4.5 divided by rest mass energy 4. So this will be 1.125. Gamma is 1.125 here. So using this gamma, we can calculate beta very easily using this relation, and beta comes out to be 0.458. Now, using this beta, we can calculate momentum. P is equal to beta E by C. Please note here, this E is the total energy, means kinetic plus rest mass energy. So P by Q will be beta E by QC. So beta E by ZEC. Z is the, you can say how much charge unit is there on the alpha particle, and E is the fundamental charge of electron, and C is the speed of light. So beta E EV, when we will convert this E in the EV, then this E will disappear from here. So we have beta E EV upon ZC. Just put the values which we have calculated the beta here, and all other values are given. And 2 is the Z on alpha particle, so we get 3.435 is the momentum. This is in EV by C units. Now when we have calculated this P, just put these all the values in this formula, and you will get the result as 2.91 millirad is the angle or change in angle in the trajectory when this particle passes through the quadrupole. Now the problem 2, in a storage ring, the betatron tune in horizontal and vertical plane is 6.2 and 7.6 respectively. What are the values of two integers which define the order of resonances for which betatron resonance can occur? Definitely betatron resonance can occur if m nu x plus n nu y or minus n nu y. It becomes an integer. Here m and n are integers, which actually defines the order of resonance also. And this is the horizontal tune represented by nu x, and nu y represents similarly the vertical betatron tune. So nu x and nu y is given 6.2 and 7.6 respectively, and m and n, these are given in these four options. So m is here 6, n is 0, here m is 2 and n is 1, here m is 3 and n is 3, and here m is 0 and n is 2. So we can make a table completely here. M is 60, so what will be the m nu x plus n nu y? It will be 37.2. Similarly, m nu x minus n nu y will be 37.2 because n is 0. So it is just m nu x in both the cases. If we will take m2 and n1, this quantity m nu x plus n nu y will become 20, and this will m nu x minus n nu y will become 4.8. And in this fashion, we can calculate the third option also and fourth option also. We can see in all these options, this is the integer value, this 20. Means this resonance can be excited in the machine. So 2 and 1 values of integers can excite betatron resonance with the given tunes. So this is basically the third order resonance, because 2 plus 1, this is order of the resonance. So 2 plus 1 is equal to 3 means third order resonance in the machine can be excited on these tunes. Problem 3 was, in a synchrotron, the strength of a focusing quadrupole magnet has been increased. What will be the effect on the betatron tunes? So first of all, we have to see that more strength of a quadrupole means a shorter focal length. Means if you are raising the strength of the quadrupole, particle will focus more tightly, means more closer to the quadrupole itself, means focal length will be decreased. And shorter focal length means more number of Betatron oscillation in the focusing plane can take. And Betatron oscillation in one turn is basically defined as the tune. So definitely if we will increase the focusing strength of the quadrupole magnet in the focusing plane, which we say generally the horizontal plane is the focusing plane, tune will increase. And in the orthogonal plane, means in the vertical plane, definitely reverse will be the true. The tune will decrease. So problem 4 is now a focusing quadrupole of strength 1.5 meter minus 2 having an effective length of 0.3 meter located in a storage ring where in horizontal plane beta function is 10 meter. What will be the contribution of this quadrupole magnet in the horizontal chromaticity? Actually, chromaticity is defined as the change in tune for the off momentum particle. Tune is defined for the on momentum particles. If off momentum particle passes through that optics, how much shift in the tune will be from the defined tune? So this is basically the formulation. Here K is the quadrupole strength. This is again the normalized quadrupole strength. Beta is the beta function at the location of quadrupole, and ds is the basically this integration is along the design path. So we have given only one quadrupole contribution we have to calculate. So ds will be just the effective length of the quadrupole. So in this case 1.5 is the k, we just put the value. 10 meter is the beta, and at the location the effective length is 0.3 meter upon 4 pi. This will give you minus 0.36. So chromaticity is minus 0.36 contribution from the single quadrupole. What is the minimum required peak RF voltage so that a synchrotron just operates? Means complete bucket may not be there, only just bare minimum, just a single particle or synchronous particle can be accelerated. That is the minimum required peak RF voltage, and neglect synchrotron radiation and other losses. So we know that momentum is just charge into magnetic field into radius. So change in momentum, if we are changing the magnetic field, it is the principle of the synchrotron. You have to keep the R constant. So if momentum changes, you have to change the magnetic field to keep the R constant. So dp by dt is qr by dv by dt. So using this, you can say the delta p in one turn. Using this relation, you will just multiply this quantity with the revolution time, you will get delta p in the one turn. So qr dv by dt, just dot over the b represents dv by dt. T revolution. So this t revolution is actually the average path length divided by the speed. So qr b dot 2 pi r b. R is the average radius of the periphery of the complete path. Now V in delta P one turn, it will be 2 pi Q R R P dot, because V delta P will give you the delta E, because E is equal to P square by 2m. So delta E will be V delta P. So and delta E is actually we got from QV sin phi, where the V is the peak RF voltage applied in the RF cavity, phi is the synchronous phase. So these two must be balanced in a synchrotron for the synchronous particle. So we will get using this balancing these two quantities. V peak is 2 pi QR, average R, B dot upon Q sin phi. Now minimum voltage is possible when sin phi is 1. Maximum value of sin phi is 1. Means phi is pi by 2. So if synchronous phase is pi by 2, we will get the minimum peak RF voltage, and Q by Q2 will be cancelled out, and this will be 2 pi R P2. This was the question asked. So minimum voltage is that which is required. For harmonic number, which of the following sequence is in general correct? Whether the betatron frequency is larger, or frequency of the RF field is larger, or the synchrotron frequency is larger. We have to see which sequence is correct. So for that, we will know what is the betatron frequency. So betatron tune actually is greater than always 1 in a synchrotron, because we have various quadrupole distributed around the periphery. So focusing and defocusing action in the transverse plane takes various times in a one complete turn. So betatron tune is much higher than the 1. And betatron frequency is definitely given by the tune multiplied by the revelation frequency. So betatron frequency is equal to tune into revelation frequency. Now betatron tune is greater than 1. So this betatron frequency will be greater than the revelation frequency. RF frequency is given by omega RF is equal to H omega revolution, where H is the harmonic number. Now given harmonic number H is equal to 1, so RF frequency will be revelation frequency. So definitely betatron frequency, because nu is greater than 1, so betatron frequency will be higher than RF frequency. And now third frequency is synchrotron frequency. So synchrotron tune actually basically the number of oscillation in the synchrotron plane in one turn, it is basically lesser than 1, because these are very, very slow oscillations. Actually in 100 or 200 turns, one synchrotron oscillation completes. So nu s is basically less than 1, and synchrotron frequency is omega s is again given by tune into revelation frequency, and this will be definitely because nu s is lower than 1, so omega it will be lesser than the revelation frequency. So lowest frequency is synchrotron frequency, and then greater to than frequency of the RF field, and largest frequency is the betatron frequency. Now momentum compaction factor depends on. Momentum compaction factor is defined by the change in fractional path length due to fractional momentum change, as we have seen in the phase focusing when we were discussing about the phase focusing. How much path is changed due to fractional momentum offset. And this is defined like this: alpha is delta L by L and delta P by P. And definitely this is generated by the dispersion or dipole magnet, because dipole magnet generates the dispersion, and dispersion actually causes this delta L. So due to dipole, this delta L by L generated. Now, if you will see the lectures, this is derived there that alpha is integration over the path of dispersion divided by the bending radius. Means how you are distributing the dispersion along the design path, alpha depends on that. In extreme cases, you can make this whole integration as 0. Then you will delta L by L will be 0. And you can say that this is the machines tuned to the values where path length doesn't depend on the momentum. And in other cases, even you can choose this integration to be negative. This is very exotic idea or exotic design of the synchrotrons, and where the alpha becomes negative. Momentum compaction factor is 0 in the case of linear accelerator. Definitely we have discussed it, and this is the true statement. Sex control magnets are used to change the betatron tune into. No, it is not true. It is false because sextuple magnets are actually used to correct the chromaticity. Betatron tune is defined for the on momentum particle, and sextuple magnet affects only the tune of the off momentum particle. Means shift in the tune is corrected, not the tune changes. So original tune remains intact. So beta tune is decided by focusing defocusing action of the magnet and is divided over the number of Betatron. It is number defined for the on momentum particle. Keep in your mind that Betatron is tune is defined only for the off moment on momentum particle. If we say machine has 9.2 Betatron tune, means this 9.2 is the number of Betatron oscillation per turn for the on momentum particles. Now, for off momentum particles, quadrupoles have different focal length compared to on momentum particle, and therefore the number of Betatron oscillation is slightly different. And this difference is actually corrected by the sextupole magnets. And the contribution of this chromaticity due to quadrupole magnets or dipole magnets, which are linear magnets, is known as the natural chromaticity. And using this non-linear magnet, actually we remove this shift. So original tune is not changed by the sextupole. It only changes the shift in the tune for the off momentum particle. Dynamics of the on momentum particle should not change using the sextuple. However, it changes, and that is the detrimental effect of the sextuple magnets, and we have to correct those errors also. But tune is not affected in principle for the momentum particle by the sextuple magnets. Which of the following contribute to the properties? Definitely the quadrupole, dipole, and sextupole. These are magnets which contribute in the chromaticity. The possible value of frequency self factor in a synchrotron is frequency self factor, as we have discussed. This may be negative, this may be positive, or this may be zero, depending whether the machine is above transition, below transition, or on transition. So it may have negative value, it may have zero, and it may be positive. Now, question 7 in assignment 8. Actually, this is the question where no option is correct basically. There is a typo mistake in the options. We have discussed it earlier also, but in this week also one student asked in the forum about this question. So I am again calculating here. Calculate the revolution time of a proton in a cyclotron having kinetic energy of 10 MeV and magnet of the cyclotron is set to 0.5 Tesla. Now, because it is a 10 MeV, so approximately we can consider that gamma is close to 1. So cyclotron frequency is omega is equal to QB by M. Just put the values. Q is 1.6 into 10 raised to minus 19 coulomb. B is given 0.5 Tesla, and this is mass of the proton 1.6 into 10 raised to minus 27 kg. So omega comes out to be cyclotron frequency is 5 into 10 raised to 7 radian per second. So revolution time will be just 2 pi by omega, and we get 0.126 microsecond. If you want to calculate more accurately, you can calculate the gamma also. In that case, gamma, using gamma in this relation 2 pi gamma m by qb, you can calculate the revolution time. So gamma at 10 MeV is just 10 plus 1000. I have taken approximately 1 GeV as the rest and mass energy of the proton. More accurate value is 938 MeV. But for just calculations, we are taking as 1 GeV. So gamma is close to 1.01. And revolution time will be here 0.127 microsecond. So here it is 1.126 microsecond, here 0.127 microsecond. So approximation of gamma is 1 is a good thing. So I think that all the questions of this assignment 11 have been discussed, and the doubt of question 7 of assignment 8 is also now clear to all. So from my side it is over.
Thank you, sir.
Rohitji, I have also shared these slides.
Okay,
to you.
sir. Great. Thank you. So, in the chat, Pratham has asked, suggest a book in which there are problems and solutions regarding each chapter.
Actually, if you will go, some books are listed in the lecture slide itself. At the end of each lecture, I have given bibliography. So I will say that Wilson is one of the book which is elementary book in the accelerators. So high energy accelerators by Wilson, you can see problems there. And also one is Andrew Wolski. Andrew Wolski is the new book, and it contains various simple problems at the end of each chapter. So these two books, I think, sufficient for my part of this course.
Okay. So, so if anyone has any more doubts, they can ask, because again I'm repeating. So this will be the last live session, live interaction. After this, I think there will be the exam directly. So if you want to ask anything, you can ask.
And Rohit, today
Yes.
Dr. Rajani Pandey is also there. So if there is any doubt about linear accelerators, they can also ask about it.
Yeah.
So in the previous live section, I suggested some one problem is mismatch with that solution. What about it?
That is discussed actually here in the last slide. I discussed that problem. Problem 7 in the assignment 8. Actually, options are wrong, and it has been discussed in the appropriate place also. So there will be no problem. Means marks will not be removed from the assignment. Okay.
Not that, sir. I'm talking about assignment 10. Hello.
I think sir has muted. So,
Okay.
which specific?
Okay. Just if I see your problem is about question 7 in the assignment 10.
Let me check the numbers, sir. Question number.
Actually, that solution has been presented in the last live session. And I think Rohitji has uploaded the slides also of that live session. So you will
Yeah,
see the solution in those slides.
yeah, and the recording is also there.
Yes. So even written solution is there in the slides for that problem.
So I'll maybe if someone is missing out on the slides, I will share the slides in the chat if you want to. This is where all the
Sir, I'm
slides
talking
are.
about the eighth question of. Hello. I'm talking about the eighth question of that assignment 10. You showed me the
Okay.
answer is 5.1, but if you go through the calculations that you showed itself, it's coming as answer of 1.1. That's what I asked in the previous section itself.
No, the answer is correct. You check again, and the answer is also provided in the live session last time. So you can see that. Slides will be shared by Rohitji.
Yeah,
So
I have
you can
shared the
see the
slide in
solution
the
in that
chat
notice
also
also.
if you
And I
want.
will again, once the solution, I will post in the forum also. Okay.
Okay, sir.
So Dhanush, you can access the slides, right? I have posted them in the chat also. You can see that, and they are also available in the NPTEL website. All the recordings of the solution and chat and the slides, so you can go through them.
And in the forum, again, I will post the solution of this particular problem.
Yeah. Okay, so anyone else has any question? Okay, Pratham, we can use the piecewise solution, that is matrix method, then why we go for Hill equation solution?
Yeah, sir, if I can use the piecewise solution, that is matrix method, then why will go to Hill's equation solution? Actually, Hill's equation gives you the very parameterization of the optics. Means you get nicely alpha, beta, and gamma. Means you have not considered the means some k somewhere is constant and then it suddenly jumps to some value and like that. By nicely you can take k variation and complete optics is characterized using these twist parameter. So that is a beautiful solution. You can characterize complete optics in terms of these parameters, and at certain location, just by looking at your alpha beta gamma value, you can actually think what kind of beam is maybe there. Suppose alpha is positive somewhere, so you just suddenly can say, oh, downstream to this point the beam may be converging. If alpha is negative, you can think over, oh yes, this is alpha is negative, d beta by ds is positive, means beta is increasing, means beam size is increasing downstream to this point. This kind of visualization of the optics is not possible using piecewise method. That's why complete solution is definitely a beautiful thing.
So Anagha has asked, sir, will we get notes or transcript of video lectures before exam?
Yeah,
So
I'd like to clarify on that point. I think notes have been already prepared and they have been installed. Now, I don't know whether the access is provided. So we'll write to NPTEL team to provide the access to the or the link to the Google Drive, which has all I think all the 36 lectures. So they will be provided in a day or two, or maybe tomorrow itself.
Yeah, many people have asked for it. So yeah.
In fact, I requested Kumud today to be present, but she is out of station perhaps. And so she told me about a week back that she has already installed all the lectures on the drive, and the link will be provided. I think we'll request NPTEL to provide the link. Maybe in this forum itself they will give the link so that all the people can either download and they can read whatever they want to do.
Okay, sir. Thank you.
And in that notes section, we have also, normally it is not done, we have also tried to do that. We have put all the PPTs also in the notes at appropriate places.
Yeah, that will be helpful. Okay, so any more question?
Rohit, I think about a few weeks back, there was a question in the forum
Hmm.
about RFQ somewhere. So that is why if there is that question, still somebody knows what is the question, then Rajni is there, she can answer it today. If suppose somebody can ask that question, I don't remember right now. Otherwise, after looking at it again, I will try to see that it is answered. But if suppose somebody is remembering it, they can ask, Rajni will answer that question right now.
So was it not answered on the forum or?
I somehow missed it. I was not in touch with that for quite some time.
Okay, okay.
So I don't know, it must have been answered.
Yeah, hello. Yeah, so the question has been answered in the forum. It's about the bunching efficiency in the RFQ.
I think Rajani is trying to say something, but we are not
Yeah,
able
hello.
to hear it.
Hello, am I audible?
Yeah, no, it's
Yeah,
better.
now we are audible.
Yeah, so the question was about bunching efficiency and it has been answered in the forum.
Correct. Now I remember it was about bunching efficiency. So it has been answered.
Yeah, it has been answered in detail.
Okay.
It's there on the discussion forum for everybody to see.
Okay.
Okay, thank you, ma'am. And so, if there are no more questions, uh, we can end the session. Okay, so one question is there from Pratham.
Why the boosting mode have fish-like structure whereas an accumulation mode has delta, EB has delta, is symmetrical. Okay, in actually accumulation or storage kind of thing, if we neglect all type of losses, we are actually keeping the same energy of the beam when it is revolving. Means we are not manipulating the central energy of the beam. Means synchronous phase should be such that no energy gain or loss should be there for the synchronous particle. So it is definitely either 0 or pi. In the case of above transition, it should be 0, and in case of above transition, it should be pi, and in below transition, it should be 0. So in if we have pi or 0 as the synchronous phase, we have complete 360-degree as the stable area in the phase. That's why it becomes symmetrical. But if we move from 0 or pi to some other value of the phase, synchronous phase, which is needed for energy manipulation. Means now if we want to change the energy of the synchronous particle, it should not be on 0 or pi. It should be somewhere on the finite voltage. Only then it will get some energy from the RF cavity. Means synchronous phase will be either from 0 to pi by 2 in the case of below transition machine, and above transition machine it will be from pi by 2 to pi. Now if we will plot potential well of this particle around this all the particles around the synchronous phase, you will say now it is not symmetrical, it is asymmetrical. As you will take 0 and 0 phase, and you will see the sine curve, it is symmetrical in minus phase and plus phase. Now you deviated it from 0 to some other value, now it will become asymmetrical. That's why now whole complete 360-degree is not available for acceleration, and that's why it become asymmetrical.
So, does it answer your question, Pratham? I think so. Oh, can you explain with graph? He wants to see some graph.
Okay, I will try to make some graph actually.
You can open the whiteboard here, or you can use the slide.
Instead of opening the whiteboard, I can also make the video on and then I
Yeah,
will
yeah,
show
yeah.
you
On
the
the copy.
model.
Yeah, yeah, yeah. Sure.
Uh, so is it visible?
Yes, sir.
So now suppose this is the RF wave, okay, which we use for particle acceleration. Okay, is it visible?
Yes, sir. Little you can use a darker
Okay,
pen.
okay.
Some.
I will use some dark.
Slightly thick pen you can use.
Yeah, yeah.
Yeah, yeah. Now it will be visible,
Yeah,
Yes.
I think.
yeah.
So now, if you're if you are not want to manipulate the energy of synchronous particle, then suppose your synchronous phase should be here. Okay. Now, if you will see from this line, you will see a complete path here of the sinusoidal wave as the complete path here with respect to this part. So symmetry is there. Now deviate the phase from here to somewhere here, okay, which is not zero now. Now here the phase is there and here you will see some positive part also here if you will go below the phase, synchronous phase. So symmetry has been broken. That's why RF bucket becomes asymmetrical. This is the case when you want to accelerate the charge particle, and it is the similarly you have in Linux also. Linux don't have zero phase because they don't have beam at constant energy. So in synchrotron, we have storage rings where we have constant energy of the beam. So synchronous phase we can have here in zero. In this case, complete sinusoidal wave is symmetric to this point. When we shift from this point, the sinusoidal wave is not now symmetrical about this point. And this asymmetry brings structural or graphical difference between the fish-like structure and other symmetrical structure. Okay.
I hope now it's clear. So, Pratham, do you have any more question? Or anyone else has any question? Please ask. He's asking about the exam pattern. So exam will be same MCQ type like the assignments, right? So, sir, do you see the chat? He's asking about the exam pattern. So,
Exam will be computer based and similar kind of questions which you have seen in assignments.
yeah.
Means there will be multiple choice and some problems may have correct answer. More than one choices may be correct in some cases, like you have in your assignment also, and it will be computer based.
It looks like instructors have given their lectures very nicely so that all the things are clear.
Yeah, and so if there are no more questions, sir, we thank you all to taking time to join these sessions and clarifying all the dots and showing, preparing the slides, and it was a very nice interaction, and I have personally learned many things, and so yeah.
We also thank you very much for nicely. We also learned a lot. We revised,
Yeah.
and for a second, I'll request all my colleagues, Amlendu and Rajni, also to put on their cameras. This is the last one, and yeah, Amlendu or Rajni, thank you very much for. And I think there is, we might have to give one more course after some time that will be on applications of accelerators. And there we will have totally different kind of participants.
Yeah, and I'll also try to be the TA for that one.
And thank you all the participants for their interest. Our interest of giving this course was to make accelerator physics more popular. Because there are a very large number of accelerators in India now. Of course, there are small accelerators, but hopefully at some stage we'll have some big accelerators also.
Mm.
I think RRCAT is going to have one for electron accelerators, and hopefully in Vizag also will have at some stage we will have this ADS program accelerator for that, which will be high current. So different kind of accelerators will be built or the will be set up, and I hope people will take interest in that. So to generate the manpower for that and the interest, that was the main motive of this course, and I think it was well received in my opinion, because in the repeat also there are 1677 participants, which according to NPTEL is very rare
Yeah,
for this kind of course. So thank you very much for everybody,
thank you, sir.
and particularly my colleagues who took a lot of pains to prepare and give the lectures, particularly to Amlendu, who came all the way from Indore to Bombay to uh, video
Thank you, sir. Thank you,
lectures.
sir, for your appreciation. Thank you.
For me and Rajni, it was easy because I think it was most easy for Rajni because her house was only some 200-300 meters away from the from that place. Mine was only 30 kilometers, but Amlendu was 3,000 kilometers, 2,000 kilometers. So thank you. I think now it looks like we can afford to close it.
Yes, sir. Sure, and
I want
see you.
thank
Yes.
to Rohit ji for conducting nicely all the
Very
sessions.
nicely. A
Very
very
nice.
cool man. Very cool man.
Thank you, sir.
Maybe you have learned this coolness from Sun Beam.
Yeah, coldest place on earth. Okay, sir. I'll see you soon again. Maybe in some in the next course in the application of accelerator physics course. I'll try to take that one too. And so yeah, till then, so goodbye to you all.
Best of luck.
Best of, thank you, sir.
Bye. Thank you.
Bye. Bye.
Thank you, sir.
I wish you all the best.
मेरा सिर रुकिए तो कर